Good morning, everyone. So, with this uh, initial lectures, I had aimed to discuss the scope of the quaternary learning quaternary geology or quaternary geosciences, and also, of course, the opportunities for a student of quaternary geology. He needs to understand the opportunities of the subject and overall the composition of the syllabus for this particular credit. So if you look at the quaternary geology itself, it doesn't signify or specify the scope. Quaternary geology means something that is related to the past 2.5 million years, precisely based on our geological timescale. More precisely, 2.58 billion years. So why this is? Because in this period, we have most of the records well preserved without any other geological disturbances. They are well preserved. Maybe little disturbed because of the human activity, but the geological records are much more observable, much more preserved, much more convincing. So if you look at the quaternary geology, then there are different aspects like the neotectonics, active tectonics, many applications, including the soil science. Amongst all these applications, the climate becomes very important in the current scenario. And that's why I specified it as the quaternary geology and climate, rather quaternary geology and climate change, because climate is there for overall entire Earth, from the inception of the Earth to the formation of the atmosphere. The climate is there that we can call paleoclimate. But how far paleo we can go? There should be some relation to the modern climate. Then only it is applicable. And the climate change, the issue raised during last 2 decades, it became, or last 3 decades, it become more sensitive because of the global warming. Global warming is there. Several events of global warming has occurred. But now the global warming in the current scenario is causing several implications to human existence, or our, it is influencing to all of us in terms of something like extreme events by which the agriculture production, by which the human settlement, by which the economy is going to influence. And because of that, then lot of scope for the study of climate has came into existence. And also, if you want to study of climate, then the geological records, they are like a book to study this climate records, climate change. The atmospheric scientists, the meteorologists, they may be studying the modern records, but definitely the past records are just like book, the history or the case studies. That learning these case studies becomes very important, because the human intelligence, the instrumentation, technology, all these things have limitations to understand the modern climate and to predict it, because it's a natural system. We really cannot understand, we cannot say at any time of the history or any time of the scientific development that we understood everything about the nature. And that's why we need to look at the case studies, look at the past records. This itself becomes a big task. The past records, to understand these past records itself becomes a big task. And that is where the scope of quaternary geology lies. Not only recording or understanding the past records, but interpretation of these past records. Not only interpretation of these past records, but its meaning in the modern context. Not only its meaning in the modern context, but the future implication, the prediction. All these things are very significant issues in understanding, predicting the climate. The understanding, then how the past records, understanding of the past records evolved. In fact, in many specialized branches of geology, sedimentology, stratigraphy, unknowingly we are understanding the climate. Unknowingly we are producing the information about the paleoclimate. The geological time scale, unknowingly it is in fact reflecting the climate change. In the geological, what is the foundation for the geological time scale? Mainly biotic subdivisions. The first appearance, last appearance of certain biota, appearance of new kind of biota, a combination of biota. How they are linked? They are geological processes, but more precisely they are climatic changes by which a particular biota is going to evolve, another biota is going to extinct, is going to become extinct. So is it not that the entire geological time scale is reflecting a climate? It is reflecting several episodes of the climate change. So ultimately the significance is already there, and we are putting forward in the form to understand the present day global warming or predict the present climate, how it is going to behave next 5 years, 10 years. So what are those things which involve in understanding the climate? Those things we can call tools of understanding the climate. The tools may be our observations of the geological records. Then beyond observation, because with observation we cannot understand everything. So beyond observation, then we need to understand the other factors of the climate, like using their chemical analysis of these records. Chemical may include simple elemental analysis, mineralogical analysis, and isotopic analysis. How the given record has behaved, responded to different climate episodes. How the climate change was imprinted in these records. So that was the main task when these science of quaternary geology was evolved, or climate studies or paleoclimatic studies. Then when you study these past records, the most important factor becomes the time. If I have got a past record and then I have studied and I derived something, these are the changes I observed, from cooling to warming to cooling to extreme warming or something like that, in a sequence. But what is that sequence? You need a temporal control, time control, not only to understand the local changes, but in order to correlate this record with the other nearby record, this nearby record with other nearby record. So we can do at least a regional correlation, because climate is a regional phenomena, rather global phenomena. So these variations has to be correlated. So that was second more important aspect, that is the dating of these records. So the early development is identification that given record is quaternary. Then to understand what has happened, to read this record. Then the latter development was to date these records, to know precisely what are the timings of these records, so that its local to regional to global relation can be established. Then later on, a time has come to distinguish between the land records and the ocean records, because ocean itself covers more than 70%, so ocean records are very important. Rather, they are the representation of the global climate. So for long time, the land records, continental records were studied very nicely. Then the quaternary geologist or quaternary geoscientist, I will say, they wanted to understand the ocean records. And there was a time, say in 90s, that many ocean expeditions were accomplished to sample these sediments, ocean sediments, considering that the ocean records are much more better than the land records. Ocean records are much more global than the land records. When people started looking at the ocean records, they found that ocean maintains a different system. The response of the ocean is different. We need to know more about the oceanography, the ocean circulation, ocean chemistry, ocean and its coupling, its relation with the atmospheric circulation. Ocean atmospheric coupling. Then if you understand the ocean records and its coupling with the atmosphere, ultimately it comes to the land record. But because ultimately we are on the land, human on the continent, they are affected because of the climate. So a ocean atmospheric continental coupling. So this coupling, COUPLING coupling, became very important in order to interrelate these records. Then several new concepts have come, that the response time, climate response time of the ocean and the continent is different. climate response time of the ocean, continent, and atmosphere is different. There can be delay, there can be advancement of certain signatures. So again, the timing has come into existence. And the heterogeneity of the effect. If something is warming at one place, it may be cooling at other place. So the heterogeneous relation, contrasting relation of different events, that became significant. And by now that we know that the climate change has become more a commoner kind of issue. A villager, an agriculturist in the village, also he will talk about the climate change. No, nowadays everything has changed. Our illiterate grandfathers, great grandfathers and mothers, they also talk about the climate change. No, during our time this was the condition, now it has changed entirely. It has become a commoner issue. Then we have already started observing all these things. Increasing temperature, successive increase in temperature, sea level rise, melting of the glacier, rising ocean temperatures, acidification, coral bleaching, everything. Altered patterns of seasonal rain in our own lifetime. You need not to ask your grandfathers and mothers, grandparents. In our own lifetime, we are seeing the altered patterns of the seasonal rain. The irregularity, we can say, in the say monsoon precipitation, summer temperatures, winter temperatures, everything is observable for the last 10 or 15 years. And definitely our crop pattern is related to all these seasonal changes in the climate, weather conditions. And if the crop patterns are changing, the productivity will affect if we don't arrange our crop pattern, arrange our crop type or agriculture, if we don't adjust our agriculture to the changing climates. So how come one can arrange this thing? An agriculturalist and a farmer also needs to understand the climate. A farmer also needs to predict the climate. So is it possible? Do we have the fundamental knowledge of predicting the climate that will link to the better productivity, that will save our loss? So this is not available with us. We cannot predict at present with the present knowledge. So now it has become an issue with the economy of a nation. Then you must have observed during last 3 years increasing frequency of storms and other extreme events, storm, wildfire globally, heat waves, severe droughts, cloud burst, all these things. So we really need to define for our text or for our course, we need to define what is climate change. And if you look at the definition also, it is very vague, very broad, very difficult to define. But IPCC, Intergovernmental Panel on Climate Change, arrived at some definition that climate change refers to a change in the state of climate that can be identified using statistical tests. So somewhat very strange definition because it is very difficult to define the climate. So we are defining the climate based on statistics. So if you are applying statistics means you are dealing with some data. If you are dealing with data means you are dealing with some records. Those may be modern records or past record. You can study past 50 years, 100 years record. Those are also past records. Those may not be geological records. We can say that those are the instrumental records. But beyond that, entirely all geological records. By changes in their mean and or variability. So in definition, we cannot include each and everything about the statistical parameters. They say variability of its properties. And this change is persistent for an extended period. We don't know that is persistent. It should not vanish within next year, next to next year, but it should be persistent for an extended period. We don't know how much we should extend 10 years, 30 years, or 50 years. Some records may be just 10 years, some records may be 40 years, some records may have long term implications, but roughly decades or longer. So, this is a definition for climate change. It has to be vague because the topic itself is very uncertain. Now, where does the certainty we can go? We can believe the certainty based on the geological records, because the geological records they already have happened, and we just need to interpret, correlate, and identify. Identification, correlation, followed by interpretation. So if you look at the geological records, the Earth has maintained a large variety of the records. Warmest of the warm events, coldest of the cold events. If you look at the geological records, then you will say, no, we are not going towards the warming. See, this is x-axis represents millions of years. 0 means present day. 60 means 60 million years back. So 60 million years back, during a time Paleocene, Eocene, or early Eocene, this green curve indicates the temperatures, global temperatures. So the warmest events were already experienced by Earth during this period, early Eocene. And this peak here, warmest of the warm, but sudden warm and sudden normalization, is defined as Paleocene Eocene thermal maxima. Earth was much more warmer than the present day condition. Why I am stressing on for this event and for this curvature? Because of the timing. This warming happened over more than 3 or 5 million years. But this warming is sudden on this scale, on the million year scale. So this sudden warming is more important because of the present day warming conditions. Present day warming, if you plot in the millennial scale, is sudden warming. Now, second important thing about this is that how different natural systems responded to this sudden warming against the gradual warming. What are these natural systems? Not only ocean, glacier, rivers, lakes, but these are abiotic systems. But the biotic system, whether there was extinction of certain species, whether there was evolution of certain species, that is the point. Now again, looking at this record much more in much more detail, you will see there are several events of sudden or gradual warming. You need to descript this time snaps, time shots. You need to understand the response of natural systems to these climate changes on ocean separately and on continents separately. Their pickedness, their continuity, their response time to different species or different abiotic systems. Now same looking at this record, Earth experienced several things like this. Antarctic glaciation started during Eocene Oligocene, approximately at after 35 million years, at about 34 or 35 million years. Sudden climate cooling was there. Now see the dimension from here to here. Rapid climate change. Then Antarctica thawing occurred somewhere during late Oligocene. Some kind of warming occurred. Then again Antarctica reglaciation occurred during about 15 million years. After that, the climate continued cooling, and somewhere during Pliocene, Arctic glaciation started. So that here during Pliocene, both the poles, Antarctica and Arctic, North and South Pole, North Pole, Greenland ice sheet was well established. South Pole, Antarctica ice sheet already well established. Even then after that, cooling was continued. Pleistocene cooling. The coolest period during entire Cenozoic, that is 65 million years, is Pleistocene. So after that, then we need to consider this into detail in Quaternary. The details not shown in this diagram because of the scale. So this describes the entire Cenozoic climate, the records of which are very nicely available. Beyond Cenozoic or earlier to Cenozoic, we generally do not go because the continental configuration, continental oceanic configuration was different because of the plate tectonics of that time. The ocean circulation should be different. The continental positions may be different. So the ocean to atmospheric ocean circulation is different. So ocean to atmospheric coupling is different. Ocean to atmospheric to continental coupling is different. We need not to imagine, because we really want to know more first, or on priority we need to know the better records which can be linked to the modern climate. So considering the plate tectonic configuration or ocean circulation, a broad ocean circulation, similar kind of conditions. So we get those conditions during last 65 million years. And that's why we may extend our quaternary studies to last 65 million years. Before that, this is just to indicate the oceanic conditions. If you look at the plate tectonics, then Indian plate was still in the southern part during early Cenozoic or during late Cretaceous, and there was ocean here. So it should be different kind of ocean circulation. There was ocean here, it is, should be different kind of circulation. The ocean might have closed here, a different kind of circulation. So we need not to go beyond this kind of configuration. This is all right to go to the past as far as possible for the past records. Now about atmosphere, how far we should go. The early Earth. Now in atmosphere we need to take certain parameter. So the most important parameter generally we can take CO2, because it is detectable in the form of proxy in the rocks. It can be interpreted, and it is one of the most common record. So using some geological evidences, this record was developed for the atmospheric CO2. Some derivation, some kind of lot of studies may be there. So if you look at the early record, then very high CO2 level, high greenhouse gases, warm climate, much more beyond the scale of the present day measurements. This fluctuated a lot. Now, because this is logarithmic scale, so we are not looking at the detailed record of CO2. We are just looking at the ups and downs of the CO2 in relation to the present day record. So you can see a lot of ups and downs and ups and downs. Earth has experienced several climatic episodes of greater intensity than entire quaternary or the present day conditions. Now just restrict ourselves to, this is 10 years, 1000, 10,000, say up to 1 million year. So in this 1 million year, how the CO2 has behaved. It shows a pattern of climate change. This pattern is marked by glacial interglacial conditions. For some time there is glacial followed by interglacial, glacial followed by interglacial. So the peaks are interglacial because warmer conditions, because more CO2 in the atmosphere, and drops are glacial. So now coming here at this position, we have already surpassed this kind of natural variation, natural variability. We have already surpassed the CO2 concentration by more than 400 ppmb. These are the scale. This is the scale for this particular record. Don't go to this scale because this is telescoped, the enlarged. So this is the variation. What is this variation? This is natural variation. And here we can say this is the anthropogenic variation. So we need to understand both the things, natural variability and this unnatural variability. So in this diagram, this is 21st century. This is average temperature, global temperatures of the earth. We consider we made it a reference point for this particular period called Holocene, from 11,000 years to say 19th century. This is also again a logarithmic scale, just to occupy the complete scale. This Holocene is preceded by colder events, -3, -4 than the average. Still lot of fluctuation and still colder event for longer time. The scale is not shown here. This longer time can be considered as glaciation, glacial time. So that this time is interglaciation, interglacial time. So we are presently in an interglacial time of the Earth. Within this interglacial time, we have already surpassed the average. And the IPCC forecast says +4 degree with band of uncertainty. We will see more details. +4 degree rise in 21st century. So within this, you can see several events have happened. Agriculture emerged at the onset of the Holocene. Means some kind of comfortable climate for expansion of human species. Then the Mesopotamia culture flourished. 2000 years back. You can see precise dates of these historical events in some more literature. Then medieval warming occurred. Viking in Greenland. A cooling event that is called Little Ice Age occurred in Europe in 15th to 16th centuries. A climatic disturbance we can call. Lot of cultural and historical events, they indicate that this little ice age was having an adverse climate to human conditions. Thereafter, some warming cooling events are there. Now we are in this state. So, entire Cenozoic is important to understand the past climate at one end, and on the other end, Holocene, that is last 10 or 11,000 years, is important to understand how human civilization or how the climate affected human. The historical records in books as well as geological records are available for Holocene. Very high resolution records are available for Holocene. High resolution is important because the models, the climate models, are nothing but mathematical models. These climate models, when you apply mathematics, you need precise quantities with little error. So if you reduce the error, as much as you reduce the error, as much as you produce the quantification, you can get better data. As much as you increase the resolution. Resolution means if you have certain data, say of temperature, of an interval of 100 years, it may not develop a good model. A temperature data of 10 years interval will develop good model. A temperature data, annual data, will develop an excellent model. Interannual, intra-annual means within 1 year, seasonal data, it will develop excellent model. So that kind of data can be obtained for this last 10,000 years, roughly 10,000 years, or precisely 11,000 years, base of the Holocene, or in a much routine language, late Pleistocene Holocene boundary, onwards from the late Pleistocene Holocene boundary. So a large paleoclimate community focused on Holocene. They found that earlier Holocene is not very significant. They might have said it is not true. Everything is significant. Entire Pleistocene is also significant. Entire Cenozoic also significant. But from the point of view of the immediate development of the models, Holocene is significant. From the point of view of the evolution of human and civilization, evolution of the human civilization and its danger towards the climate change, these last 10 or 11,000 years are significant. Then the adaptability, human adaptability, if you compare with the other species, probably similar kind of things are there, but the other species, they do not react, they do not oppose to the climate change. We human, we oppose to the climate change. We try to develop the technology and further worsen the conditions. that has to be noticed while doing any remedial changes for adopting the climate change. We need to be sustainable, and this is probably understood in recent years by human. The sustainability. We need to develop our sustainability to accept the earth conditions. And regarding the impact of the climate change to human health, to all everything, all the other conditions, also demand a sustainability. The development should be sustainable. And finally, if we want to learn something, if we want to study, do research, we need funding. To flourish the subject, we need funding. That is our academic point of view. So if you look at the impact of this kind of studies, if you don't do this kind of studies, there are great economic loss. If we go on adopting similar practices, we don't study climate, we don't interpret climate, then there are great economic losses. Number of disasters that will also cause economic loss. And such reports are available. I cannot go into detail, but such reports are there. In case of India, India is ranked 6th most vulnerable country in the world to climate change. We are not talking about the several other countries, even the coastal countries like Bangladesh, Madagascar, or many other countries. So economic means social is also there. Social impact is also there. So we need to understand the causes and effects of climate change in a much more complicated way. This flowchart is still simpler, but it mentions three things. It tries to integrate these three things: the causes of climate change, the effects of climate change, integrated by feedback. We need to understand the feedback mechanism of climate change. Number of things are there: human induced or natural system, and their effects on humans. What is more important is the to understand the feedback mechanism. It can be anything. It can be considered individually or also several parameters combinedly. Feedback can be, the example, the solar radiation, sunlight reflected from the snow will be different, then from the water will be different, then from the land will be different. So same sunlight will have different feedback mechanism over a snow cover, over ocean surface. Also different response time over ocean and over snow. Probably the snow cover will reflect more sunlight. It will not absorb, it will immediately reflect sunlight, so that the warming may be less compared to the oceans where the sunlight will be absorbed by the water. So the feedback mechanism of the ocean will be different than the snow. But these two things are not independent. They are linked by atmospheric circulation. Not only linked by atmospheric circulation, but the snow melting will give rise to a lot of fresh water to the oceans. Ocean salinity will change. Ocean salinity along with ocean temperatures will give different kind of results. So these kind of things are called feedback mechanism. How one system is feeding back to another system. That is the feedback mechanism. And ultimately, we are not doing science, just fundamental science, but its effect on human is very important. That is our survival. And then several such news reports, magazine, and all these things, they give a lot of information, quantification to alarm us, and also they produce interpretation, but based on definitely some data, its effect on the economy, nation, or human society. There can be several arguments, but we need to be careful with whom we should hear the arguments. Are they the natural scientists? They have certain background of, say, quaternary geology. Are they climatologists? Are they atmospheric scientists? All these things we need to understand with whom we are gathering the information. We need to be more scientific. We need to be data based. And that's why this subject becomes very significant. One of the important aspect is the agriculture or commodity. That includes not only the agricultural production and pattern, but the ocean related commodities on which our survival, on which our economy is based. Then several such data from the World Bank reports, you will find several such assessments which are already warning us. This is one database that indicates deaths from the heat in case of India that have raised since 2015. Beyond that, the data is not available with this slide, but sudden increase in 2015. Hotspot like situation is increasing in India, central part of India. It's becoming hotspot. Some data may be up to, again, up to 2015. Beyond that, it is not there. We need to gather that data. We need to find out that data. It should be available. And these are the commodities. Commodities, rice, wheat, maize, all these things, they can have positive as well as negative effect. In response to climate change. So whatever may be positive or negative, but they are disbalancing the equilibrium. The present day conditions, if we say these are the equilibrium for which we are habitual, that is being disbalanced. A kind of disequilibrium is being created. That may not be important for geologists, but it is very significant to the national economy and social aspects. Whether we need to change the agriculture pattern or we need to adopt something that is a national issue, socio-economic issue. Then several natural conditions. The most important may be sea level rise, 1.3 mm per year. Sea level is rising. Increasing cyclonic disturbances, increased annual precipitation, warmer seasons, freshwater supply, high variability in this freshwater supply or yields. All these are also commoner factor which are essential for the stability of a nation. This is now information related to India developed from the Indian Network for Climate Change Assessment, INCCA, an agency that is assessing the climate change related to India and its impact on forest and natural ecosystem, human health, and the agricultural productivity. And the risk India, we have disaster ministry for the disaster management. So that needs to evaluate the disasters not only by earthquakes, tsunamis, but also by climate, also by the climate change. Disaster to ecosystem. It includes everything. The ecosystem. So if you look at this, already we have seen heat waves may intensify in the central part of India. Himalayan glaciers will melt and will produce a lot of fresh water, but rather floods. Sea level rise here will affect most. Sea level will affect the entire coast of India. There can be increase in coastal erosion. Coastal regions will also experience a lot of cyclones, storms, and some of the niche areas where little change in monsoon affects a lot is like this. Very sensitive crop production, very sensitive monsoonal condition. It will affect this region. Then again, several such reports are there. As I said, most important may be the sea level rise and the submergence of some of the most populated or most important cities. All these red color are going to submerge. How they have projected 30 to 60 centimeter rise by 2100. Nearly certain events, even if carbon emission are sharply reduced, even if you control the carbon emission, even then you cannot really control the sea level. 60 to 100 centimeter rise if emission continue to increase. And if the levels rise by 50 to 50 centimeter, 45 cities in India with 5 lakh plus residents will be flooded. Cities like Mumbai, Kolkata, Surat, Chennai, New York are having the greatest threat. Hello. हाँ गुड मॉर्निंग. हां हां माझं लेक्चर चालू आहे सर. मी येईल आता 10 मिनिटात. हां ओके. हां ये ये ओके. So we'll stop here. You will be ready for the next lecture. We'll continue with this scope. But I want to point out that you have to be very you have to be very broad in thinking when you talk about the climate change. We cannot restrict to some subject. Climate change is not restricted to anything like geology, meteorology, atmospheric science. It is an objective. To understand that objective, we need to understand the natural system. So thank you very much. We'll continue next time.
Thank you, sir.